Welcome back, everyone, after the very short break. So, as already announced, we are in this program, we are going to have a mini or not so mini course of 8 lectures on the topic of optimal transport and high dimensional probability. And it's going to be delivered by Yair Shenfeld from Brown and Sinho Chevi from the IAS. So Yair is with us here today. He's going to deliver the first lecture. So with these few words, I would like to hand over the session to Yair, and we are all eager to hear about optimal transport.
It's kind of elementary, so maybe for the expert it could be boring, but that's okay. So the main problem here is that my handwriting. So if you have a complaint, that's totally okay. Just tell me, and I'll try to improve it. Other than that, everything will work perfectly. It has to be. Okay. So I should say that most of the, not all, but most of the lecture that I'll give, I'll try to follow a textbook by Villani. He has 2 textbooks. One is called Topics in Optimal Transportation or something like that. And that was the first one. And then the second one was Optimal Transport Old and New. So this is going to be more from the first one, which is kind of friendly and shorter than the first one. And this, so just the references for this lecture will be roughly, let's just put V for Villani. So it would be roughly the first chapter and maybe a little bit from the second chapter. Okay. So before we talk about optimal transport, let's talk about what does it actually mean to transport one probability distribution to another. That's the basic question. So, and of course, feel free to ask questions. So we imagine that we have mu and nu, which are probability distributions in some spaces. Let's call them x and y. Most of the talks, x and y are just going to be, even x is going to be equal to y and just going to be the Euclidean space. So from now on, you can just pretend that that's the setting we're working in. So we're going to say that a map T, which goes from x to y, transports mu to nu. So we're kind of going to write the definitions in multiple ways. But maybe the set theoretic definition, measure theoretic definition, is we just say that the measure of a set B, so here B is assumed to be a measurable set in Y, the definition of it is, well, sorry, rather we have equality, where here by T inverse we mean the inverse image. So we do not assume that T is invertible or anything like that at this point. So T inverse just means the inverse image of the set B. So the inverse image of the set B is some set, measurable set inside X, and we will say that T maps mu to nu if we have this equality. And I'll write this definition in some other ways. So maybe probabilistically we can say that if we have U, which is sampled according to mu, and we have V, which is sampled according to nu. Sorry, if we have U, which is sampled according to mu, then T of U is going to be sampled according to nu. That's another way of saying that T maps mu to nu. So to see that, just let's look at what is the probability that T of U is contained in some set B. So we will just move the T inverse. So we take the inverse image. But by definition, this is just mu of T inverse of B, because U is sampled according to mu. But that's, as we said, that's just a definition of nu of B. So maybe probabilistically the easiest way to think of a transport map is just to say, if I sample my original random variable according to the one measure, and then I apply the map to it, then the law of t of the original random variable is going to be according to the target measure. That's the definition of transportation. Any question? So this is kind of important to understand because that's one of the basic things we'll work with. So let's do some really trivial examples. So let's actually do maybe a discrete example first. We just have some discrete set of some elements A1 to AM. And let's say mu is a delta. It's a Dirac mass on AI. It just means that it's deterministic, meaning you choose AI with the probability 1. And nu, let's say, is delta AJ, where AI is different than AJ. Then what would be a transport map? Then you can just take, so you can take T of AK to be equal to AK if K is different than IJ, and then T of AI should just be equal to AJ, and T of AJ should be equal to AI. Because then if I sample first according to mu, I will get AI with probability 1. I apply the transportation map to it, I will get AJ, which is sampled according to nu. Okay? So this is a very basic example. Let's do another example. Let's say now we work in Rn. And let's say our measure mu is still deterministic, so just a point mass at the origin. And let's take nu also to be deterministic, but it's going to be at some other point, which is in Rn, but not the origin. So then we can just take T of x to be x plus a, and that would move mu to nu. So let me ask you, what other two distributions would be so that this map T would map one to the other? Here we show that this linear map takes one Dirac to another Dirac, but I claim that there are two other distributions which are less trivial than that, and where this would still happen. So, Gaussian? Yeah, exactly. So you can take a centered Gaussian and then another Gaussian with the same variance, but just centered at A, and this would still be a transport map between one to the other. Okay. They don't have to be unique, of course. Let's think of the following example. Let's say that again we have x is the same as y, and is this discrete set. But now let's suppose that mu and nu, they're both simply the uniform measure. Then what could t be? If they're both uniform on the discrete sets? Any permutation, exactly. So any permutation would do the trick, because if you sample uniformly from A1 to AM and then you just take some permutation, it's still going to be uniformly sampled. So you can see it's not unique. Maybe an example which is kind of a similar nature is we can take maybe x equal y equal to Rn, and let's take mu and nu to be the standard Gaussian, and then we can take t to be rotation. Because if you just let's say you do you rotate the Gaussian, it's a centered Gaussian, it's still going to be a Gaussian. Okay, so the point is the transport map are by no means unique. There are many ways of going from one measure to another. We will be interested in kind of the best map in some sense, and I'll explain what do we mean by that. That's why we call them optimal. But maybe just before that, let me just write another, just two more definitions. Maybe I can erase it here. I want to write two more definitions of what does it mean to transport between one measure to the other. So the first definition is basically equivalent to the first one, and it's kind of functional in nature. And it just means that, so I'll be a little bit vague here, but we want to have the identity that if we take psi. So psi is going to be some test function in some class which is rich enough. You can think maybe, let's say, all continuous and bounded functions, something like that. So if you take this psi and you compose it with t, remember t goes from x to y, and you integrate with respect to nu, that's the same as integrating with respect to nu this map psi over y. So it should be for all, I say for all psi, we mean for all psi in some large enough class. So that's another way of saying what it means to transport one measure to the other. So maybe a little more specific, let's think of the case where x, let's say with Euclidean case, then let's say that mu and nu are absolutely continuous with respect to the Lebesgue measure. So that just means that they have densities. Let's write them f and g. So here we write d mu is equal to f dx and d nu is equal to g dx. Then from this formula, you can see that they're what we call change of variables formula. So you can write an identity for the densities of these two measures. And the way it works is that you need that f of x to be equal to g of t of x, and then the absolute value of the determinant of the derivative of t, an absolute value. Okay, this is just the change of variables formula. So to say that t maps f to g, or rather mu to nu, would mean that it would satisfy this identity. Of course, here you need some regularity. So it's not, these definitions are not as general maybe as what's going on here. You need some regularity, but it's something which is definitely be important for us, and it's good to keep in mind. It gives another way of thinking about transportation. Okay, so this is just what it means to transport one probability measure into the other. But as I said, we care about an optimal way of doing so. So what do we mean by optimal way? So this story goes back to Monge, who was a French mathematician. I'll write out the problem in a bit, which is in a way which is a little bit more general than what he wrote, and then I'll write down his original formulation. But the setting is as follows. So this is the Monge problem. We imagine that we have this function c, which c for cost, which goes from the product of Cartesian product of x and y into the non-negative number. Then, okay, in some setting it can be even infinity, and some people care about such things. For us, it won't be as important. And what we wanted, and let's say, for example, we can think of, let's say x is equal to y. Let's do an example. It's going to be some metric space. But again, you can always think of Euclidean space, and the metric is D. Then a good example of a cost function would be c of x of y. It's just going to be the distance between x and y raised to some power p. That would be a canonical example. And p here is going to be greater than 0. Well, let's maybe take it greater than 1. You can make sense of the greater than, okay, let me say p greater than 0, but there are different behavior depending if p is greater than 1 or smaller than 1. You can even define what it means, like dxy to 0. You can just define it to be what we call sometimes the trivial metric, which is just 1 if x is different than y and 0 otherwise. So it makes sense to define it that way. But anyway, once you define this notion of cost, which you think of it as how much it costs to move something from x to y, the problem is, given mu and nu, we want to minimize the integral of the cost, where in the first coordinate we will put x, here we will put t of x, where we integrate with respect to nu, and here it's over maps which send mu to nu. So maybe I just forgot, just read some notation. We write t, this is like a push forward, we can write like that. Sometimes it's written like that. Okay. And I'll write sometime just this notation, just to mean that mu is or like this, going to nu. Okay, so what is going on here? We imagine that we have like two piles, of like sand. This is mu, and this is nu. And we're going to move this pile to this pile. So we're going to move it 1 grain at a time. And the cost to do it is to go from x, so this is some point x here, we're going to have an amount of mu x, is going to be on top of it. So maybe let's say we have x, so here it's mu x. And we need to move this amount with this map t to the point t of x. And we want to do it in such a way that the cost that we pay is as minimal as possible. So there are many map t that would take us from u to nu, as we said, and we want the one which minimizes the cost, where the cost here is measured per unit mass, which we measure by mu of x. We have to move it from x to t of x, and that's the cost that we pay. And a natural cost would be to just take the distance between them, raised to some power. Does it make sense, the setting of the problem? Okay. So just maybe to do some trivial examples. Let's again go back to our measures, which are just deltas. So let's say that nu is equal to some Dirac at a point A. Then in that case, we need T of x to be equal to A for every x, right? The entire mass has to be concentrated, has to be pushed forward to this one point A. Because we're going from some probability measure, think of maybe a Gaussian, and then you push all of it to one point A. So T of x has to be equal to A for every x. And that has to be true for any transport map. It doesn't matter which one you choose, it will have to do that. So then if we look at C of x, T of x d mu, it would just be the integral from C, it would just be the integral over x, and then just the cost function Cx comma A. Yeah? So if we want to do like a sub-example, so if we take mu, let's say itself to be a Dirac mass, let's say at some delta B, then the cost is going to be, so we're going to have C of x, T of x, d mu of x is just going to be CAB, which is, for example, just the distance between A and B. So the cost is just how far is A from B. This is, again, an example, because you can take other cost function. Okay. But maybe just to note already the issue, it is not always the case that you have a transport map between two probability measures. Because let's think of the following example. Let's take again mu to be a Dirac, let's say at the origin. But now we take nu to be the following mixture. So what do we mean by that? This is just the measure where with probability a half, you would have a point at A, and with probability a half, you would have a point at minus A. Of course, A is not there. So why can't you have a transport map from u to nu? So the point is that the mass has to be split, right? But this transport map cannot do that because T of A will just be sent to some point, wherever it is, and that's what the, so if you think of, again, if we think of T of U, and U is sampled according to mu, which is just as Dirac math, this is going to be with probability 1, it's going to be equal to TA, and of course this cannot be distributed according to nu. So we see there are even instances where you don't even have a transport map. So in that setting, in that sense, this problem is kind of problematic because for certain probability measures, you don't even have existence of solution. And this is before even talking about the type of cost that you take. You can take whatever cost you want, and we're already in trouble. For an historical comment. What was the setting of Monge? What did he care about? He cared about, of course, he worked in Rn, probably R2, to be fair. And he took C of x, Cxy, it's just a Euclidean, but it's really, you take the L1 norm. Or let's just say in dimension 1 even. You would take just the absolute value of x minus y. Let's just even pretend in dimension 1. And we will see that the power here that you take, we said that you take power p, we'll see that that power it actually matters. Okay, good. So I've explained the issue with this Monge problem because it's clear that sometimes you don't even have a solution, and I want to tell you how do we go about fixing this problem. But let me maybe just write an exercise, so there won't be any homework or anything like that in this mini course, but sometimes it's good to, yes? Is defined? Yeah, so assuming there is even a map, find the one that minimizes its cost. The goal is to find T, but when you say T, we mean assuming there is such T, of all of them, find the one that would minimize this. Yeah. Of course, it might be unique, okay, but forget about unique. But the problem is to find that T, exactly. Could be? Absolutely. I mean, linear is very much the exception. It would almost never be linear. In fact, this is good. This brings me to the exercise that I wanted to show. So I'll give you an exercise to find. I'm not going to ask you to prove that it's an optimal transport map, but it's going to be an exercise for you to show that it is a transport map, which I can tell you it's the optimal one in dimension 1. So let's just see what they look like, and we will see that they're definitely not linear. So, okay, like I said, there are no exercises in this course, but I can give you some things to try if you want, and computation can be fun, especially if they're formal. That's the best part. So let's try to do that. And if you're having trouble, of course, come talk to me or to Sinho. So this is just okay. So let's do an exercise. So let's work in the setting of just R. And let's suppose that mu and nu are both absolutely continuous with respect to the big, which means that they have densities. And you can assume that the densities are smooth. We're going to make them as nice as you want. So originally I thought of just giving a hint, just saying find T, which goes from U to nu, using the CDF, the cumulative distribution function of the random variable. But you don't take it for credit, so why? No need to be annoying. I'll just give you the formula, and then you just have to verify it. Okay? So I claim that you should check that if you take the inverse of the CDF of nu and you compose it with a CDF of mu, you will find that this map transport mu to nu. And this is actually also the optimal transport map as it happens for a certain cost. But okay. Is it clear, the exercise? But just to go back to your point, this is definitely not going to be a linear map. Okay, good. So how do we go around this Monge problem? So the answer is the Kantorovich problem. You solve one problem by another, which is what usually we do in math. I say it like that. Historically, it's not that Kantorovich tried to solve the Monge problem. He was interested in it for a different reason. Later, people realized that, okay, this actually solves, it's a way of addressing the Monge problem. I should also say that Kantorovich, so they're going to, for the same reason that we explained before, where you think of this transport problem as you try to move mass from one point to the other, you can also think of it as you have resources. Maybe you have like coal, you have coal mines. At the time, that's what people were interested in. They had coal mines spread in different parts of the country. You had factories that need this coal. So you have to take some coal from some factory and move it, one mine and move it to a factory, and you have to decide how to do it in the way where you minimize the cost of transportation. That's a problem that Kantorovich was interested in. That was in, I think, the 40s in Russia. And what's very beautiful about it, not only did he find a way to formalize it, he formalized it in such a way that will become clear. It's something called linear programming. And so he invented basically linear programming, which is extremely important in applications. And he ended up getting a Nobel Prize in economics for this work. So it's quite an interesting story. So let me show you what is the Kantorovich problem. So to explain the Kantorovich problem, I have to explain the notion of a coupling. What does it mean to couple two random variables? And for this we would think of a coupling as a way of extending the idea of transporting between two random variables. So it's probably something that you're familiar with, but let me just remind you. So a coupling, we'll call it pi. Of mu on x. So I'm being a little brief here. So I mean the probability measure mu on a space x, and similarly for nu, is a probability measure on the product space, so on x cross y, such that the first marginal of pi is mu, and the second marginal of pi is nu. So that means that if we look at pi of A, and we take the product here with y, this would be mu of A. So A here is a measurable set inside X. And similarly, if we take X here, and here we take a set B, we're going to get nu of B. And B is a measurable set in Y. So probabilistically, if we have U, which is sampled according to mu, and we have V, which is sampled according to nu, then V is going to be sampled according to pi, and this is just the joint law of mu and nu. So why is this a generalization of the idea of transportation? Well, imagine we had a transport map from mu to nu. Then one example of a coupling pi would just be to just take U, which is sampled according to mu, and then here to have T of U. And this would be sampled indeed according to pi. That would be one example of a coupling. So in that sense, it's an extension, but what's nice is that we can always find such coupling. Unlike in the case of a transport map, where we saw that sometimes we just don't have a transport map, we can always find a coupling. Why is that? Why do we always have a coupling between two measures, mu and nu? Exactly, because you can take the product measure. You can always take pi equal to the product between mu and nu, which probabilistically just means you take U and V to be independent. That's one example of a joint law. It's the simplest of all of them. Actually, in some sense, you can think of it as the opposite extreme of a joint law of this form. Because if I think about all the possible joint law between two random variables, in one way, in one extreme, they're completely independent. In the other extreme, they're completely correlated. I use correlated in quotation. I don't mean correlation in the definition. But what does it mean to be completely correlated? It means that if I know U, then I definitely know V. And that's the example of a transport map. So this example is on the one extreme, and the product measure is on the other extreme. But what's nice is that even though this might not exist, we can always take the product measure. So the set of coupling is just bigger than the set of transport map. So that's why it's a relaxation. So let's see. Now that we have coupling, we can actually talk about the analogous problem to the Monge problem. So let's see what it is. So now the problem is to minimize over pi. So we're going to use this notation, pi of, this is big pi of mu and nu, just to mean the set of all possible coupling between mu and nu. And we will minimize, again, the cost, cxy, and this is over the product space, and we're going to integrate against this joint law of pi. And again, you can see that if we are in this example, if pi is indeed of this form where it is built from a transport map, then this cost would be exactly the cost that we had in the Monge problem. Because in that case, y is just going to be equal to t of x. And then we're exactly in the Monge setting. Is that clear? What is another advantage of this problem if you stare at it? Can you see from the perspective of optimization problem, why is this a better optimization problem? That's right, it's linear, and it's linear in our optimization variable, which is pi. In the problem, in the Monge problem that we had before, we had this c of x tx d mu of x. Clearly, this is not linear. So, and here the variable was t. We're trying to find t that would minimize that. This is not a linear problem in T, because C can be, very complicated, but even if it's quadratic, let's say, one example that we would look, that Sinho will talk about in the next lecture would be x minus tx squared. Okay, pretty nice, but this is still not going to be linear in T. Here, on the other hand, it doesn't matter what the cost is. The variable, this optimization problem is linear in pi, which is our variable. Now, of course, this is going to be in general, if you look for probability measures on our end, this is going to be an infinite dimensional linear program. So you have some issues with infinite dimensionality, but that's okay. That's a more like formal issue that one has to work with. But the basic structure is that it is a linear program. And then specifically, if you work in discrete setting, then this is like a valid finite dimensional linear program. Okay? Just to maybe, okay, I don't know if it's worth belaboring the point so much. We already saw that that looking at coupling is a generalization of transportation. But just another example maybe. Suppose we had T1, suppose we had two transport map which send mu to nu, then you can build coupling from these two transport map, because you can just take T pi, okay, and this is a good opportunity to introduce some notation. So what we're doing here is we're basically either using the first transport map or we're using the second transport map with probability a half. So when we write ID cross, let's say T1 sharp mu, we mean that we're transporting the probability measure mu by this map, which is in one component it's the identity, and in the other component is T1. So what this map would do when it pushes forward mu, in the first component you will just get mu, and in the second component you will get T pushing mu, which is what you want. So this is going to be a probability measure on the product space. So we're taking the measure mu, which is supported on X, and we're pushing it by a map which has two components, and therefore we get a probability measure on X cross Y. And when we push it by something like that, the first component is just the identity, so that would just push mu to mu, which is what we want, because we want the first marginal to be mu, but then the second marginal will be pushed by T1, which is what we want, because we assume that T1 pushes mu to nu. Does that make sense? So, for example, if you had two of them, you can just mix them, and that would give you another joint law. Okay. So let me maybe do I have until 4:30? Oh, okay. let me write out the problem quickly just in the discrete setting. And then if we have time, I don't think I'll have time to talk about duality, which I wanted to talk about, but hopefully I'll have a little bit of time of just giving you a quick review of what will happen in the coming lectures. So let's do the discrete case. So let's say that X is just a collection of points, x1 to xm, and Y is also a collection of points, y1 to ym. And let's take mu and nu to be uniform. So what do we mean by that? We mean that mu we can just write as a sum from 1 to m. Here we have to divide by m. And then the deltas on each of the xi. So delta xi with probability 1, you will sample from xi, but then we're summing up over m of them and we're dividing by m. So that means that with probability 1 over m, you will sample from each of the points. And similarly for nu. But we're going to put them on yi. Okay, so if we're in this setting, then what happens is we can identify this coupling with matrices. And the way it works is, so this set of coupling between mu and nu, you can identify it with matrices, so pi ij, with the properties that first they have to be non-negative. If we sum each one of, so if I fix a j and I sum over all the I should get 1. And similarly, if I fix an I and I sum over j, I should also get 1. And how can we think of it as a joint law? The connection is just that we can just write that pi ij, we have to divide by m. Just think of it as a probability that u is equal to xi and v is equal to yj. Again, u and v are just going to be, u is uniformly sampled on x1 to xm, and v is uniformly sampled on 1 to 1m. So the point is that if you want to describe completely the joint law of these two uniform random variables, you can just specify it by choosing a matrix, which is going to be an m by m matrix. So the entries are always non-negative because they're supposed to be probability, because it's a distribution. Why do they, so why is it that for each row and for each column they sum up to 1? What are we capturing by that? Maybe it would be easier if I wrote 1 over m. Because remember, I'm just dividing by m at the end. So if I wrote 1 over m, what would I be capturing by making this requirement? Say again? Exactly. We're capturing the fact that the marginal distributions are uniform. Because when you sample each row and you sample each column, so it should be really 1 over m would be easier to think about. So then the way to think of this pi ij is just the joint law that u is equal to xi and v is equal to yj. So there are many such matrices. So if we, so what does the problem become now? In this setting, the Kantorovich problem. So now the problem becomes to minimize over these matrices pi, and then 1 over m sum ij equal to 1 to m, cij pi ij. So cij just means the cost xi comma yj. So cij just c. But now you see this is like a really legitimate linear program in the variables pi ij. You can just, you can even write it as, just an inner product between C and pi, where the inner product just means the trace. So you take the trace of the two matrices. Okay, but you're minimizing this linear function over some set pi. The set pi, which is a set of all these, let me just remind, is a set of all of these matrices. But the set of all these matrices is going to be a convex set. So when you minimize linear functions over convex sets, where does the minimum occur? Exactly, it occurs at extreme points, right? So the picture is if you have some polytope like this, and you have a linear function which you minimize, the minimum will happen here. And why does it happen here? Because if it happened in the interior, because it's linear, I can just push it a little more until I hit the boundary, and once I hit the boundary, I can push it a little more in this way and this way until I get to the extreme point. Okay, so what are the extreme point of these type of matrices? They're permutation matrices. You can generate every matrix that satisfies this constraint by taking convex combination of permutation matrices. So therefore, you can replace the infimum over the entire set just by the infimum over sigma. So sigma, we mean the permutation. And then it's just going to be I equal 1 to m c xi y sigma I. So that showed you how how you can address this type of linear program and solve it in the finite dimensional case. And this type of expression will show up in the second lecture. So that's why I wanted to write it down. Okay. So maybe, okay, here's maybe what I'll do. I'll sketch just in words. Okay, I'm really, it's not really going to be a proof. I'm just going to tell you how people do it because it's kind of technical and standard and not that interesting. But how do you prove that you always have existence to this linear program, to this infinite dimensional linear program? And then once we're done with that, I'll tell you what we're going to cover in the coming lecture. So the theorem is that, so I'll write this problem always has a solution. Unlike the Monge problem, remember, because sometimes in the Monge problem we didn't have a transport map, let alone an optimal one. And the way to do it is, so you show that the objective, so the objective functional, so by that I mean this. So this is a functional which takes pi and gives you a number. The objective is lower semi-continuous. This we'll recall what it is in coming lectures, but you can just think of continuous for now. And that the constraint set is compact. So we know that if you minimize a continuous function over a compact set, the minimum will be attained. So you have to say, okay, what do we mean by continuity? What do we mean by compactness? What are the topologies here? So the right way to think about it is to think about weak convergence. So we'll remind you in coming lectures what it is, but weak convergence of distribution just means that we say that mu k converges to mu weakly if the integral of d mu k converges to the integral of d mu, where psi is continuous and bounded, let's say. So that's the type of topology that we're talking about, and that type of compactness that comes from this topology. And so the work is to show that this constraint set, which is the set of all these coupling, is indeed compact with respect to this topology, and also to show that this functional is continuous, but that's easy because it's linear. So that's how the standard way of showing that you always have a solution to this problem goes. Okay, so let me, in the remaining 10 minutes, probably I won't need all of them, but I'll tell you just where we're going from here. And please let me know for the coming lectures whether this was too fast, too slow, or just right, things to improve, because now it's the time. So lecture 1 was what we just covered. So outline. So lecture 1, that was me, Yair. And that was, let's say we did optimal transport, just the basic. So lecture 2 will be Sinho. And so he'll do a couple of things. So as we said, this Kantorovich problem is a linear programming. What do we know about linear programming? Well, there's basically only one thing we know what to do with linear programs. What is it? Okay, yeah, that's how to solve it, use a simplex algorithm, but what is maybe a mathematical tool that we have to handle linear programs? Duality. There's nothing else. Okay, maybe I'm exaggerating. But duality is one of the important, maybe the most important tools that we use in linear programs. So we didn't really derive duality here, but Sinho will show how to do duality, which is very important in this setting. So duality, there are different ways of proving duality. I was hoping to have the time to show you how to do duality by a min-max argument, and you can try it on your own. It's really, you can just do a formal computation. If not, come talk to me. I'll tell you what I mean by that. So there are different ways of doing duality. Sinho will use a more geometric approach, which is called cyclical monotonicity, which is very important because it also helps you prove a very interesting theorem, which is called Bernier theorem. And what this theorem corresponds to, at least at the basic level, is if you look at the case where x and y are the same and they're equal to Euclidean space, and you take your cost to just be the Euclidean distance squared, then Bernier, under very mild assumption, can actually solve the Monge problem. Not just the Kantorovich problem, but actually the Monge problem. And not only that, it can also characterize the optimal transport map in a certain sense that I don't want to tell you, not to ruin the surprise. Okay. So that would be lecture two. In lecture 3, so that would be me again. We will talk about the Wasserstein space. So first, I should say the Wasserstein is like a very controversial name. A lot of people, I think especially Russian, they really do not like that name because it kind of takes away from Kantorovich. And I think historically people claim that Wasserstein didn't really, but I'm not going to get into it, and that's just a name that's stuck. Yeah.
Well, in German, it means waterstone.
And? And are you saying that that's connected to? I think it's the name of an actual person. It's not just the.
I'm just saying that it also means waterstone.
Right. So maybe, yeah. So what is this Wasserstein space? The point is, you can actually define, you can take this objective function that we talked, and you can actually use it to define a metric between probability distributions. So you make the following definition. Let me just do it in the case of 2, just to simplify. So the way you would define the squared, okay, maybe let's do the square. Okay. The way you would define the distance between 2 probability measures, you would just take the minimum coupling of all these coupling nu and nu, and then let's say x minus y squared d pi xy, and then I guess we have to take a square root. So this is a non-negative quantity. Okay, that's fine. But the point is that it would actually be a metric in the sense that it will satisfy the triangle inequality and the other property that we need for a metric. And now we can talk about the space of all probability distribution with a certain metric on it. And we will want to understand this metric. And I will also show you how this metric is actually related to the notion of weak convergence, which means that 2 measures being close to each other in this metric is very much connected to other notions of closeness that we use in probability. So now we can talk about this as a whole space. So that would be in lecture 3, but then in lecture 4, we will see that, which Sinho will give, there's actually much more structure to this space, and you can really view the Wasserstein space in some sense as an infinite dimensional Riemannian manifold. So this is Riemannian manifold. And this is related to called the autocalculus. So in that way, we can start talking about geodesic and such thing. What is the shortest possible way of going between two probability measures? There's the dynamical way. I'm saying things which are not very clear now, but will become clear in that lecture, of writing this type of metric. And then you can start doing calculus on the space of all probability measure. So now you can take a functional, which takes a probability measure and gives you a number. For example, entropy. Entropy is something which takes a probability measure and gives you a number, and you can start talking about the gradient of that functional with respect to this metric. And once you talk about gradient, you can talk about gradient flows. You can start running gradient flows in infinite dimensions, and this will be related to a more familiar object like Langevin dynamics, heat equation, and things like that. So this is actually lecture 4 plus 5, so 5 would be more gradient flows. Okay, so this is kind of the optimal transport part of the mini course, but we haven't talked a lot about the high dimensional probability. So in lecture 6, we will start connecting between all these autocalculus type stuff and functional inequalities. So functional inequalities are one way of capturing various behaviors of probability distribution. So in lecture 6, we'll explain how do you go from functional on this Riemannian manifold, infinite dimensional Riemannian manifold, into getting functional inequalities. And then in lecture 7, we will kind of continue this discussion. So maybe just example are LSI. This is something called Log-Sobolev inequality. W2, this is something called Talagrand's inequality. These are all examples of functional inequalities. And then here in lecture 7, we'll show how these functional inequalities are related to what we call concentration of measure. So for example, we'll talk about sub-Gaussian random variables. So sub-Gaussian random variables are just random variables that kind of behave like a Gaussian. They have the same tail as the Gaussian. So we will learn of how to find ways to show that a random variable is sub-Gaussian using this functional inequalities. We'll talk maybe if we have time about tensorization, which is an important principle in high dimensional probability. And then in the last lecture, Sinho it will be more of kind of a more applied example of showing how to use all this machinery to show how you can analyze the Langevin dynamics. So the Langevin dynamics, in this context, you can think of it as a way of sampling from a probability measure. There are different, we want to sample from a measure in many applications. There are many ways of doing it. Langevin dynamics is one of the basic ways of doing it. We want to understand how good the sampling algorithm is, and you can do it using this machinery that we developed in the previous lecture. So I think I'm just about out of time. And please, again, if you have comments, please come and let me know. That would be a good time because it's the first lecture, and of course, any questions. All right, thanks.
Thank you for the great first talk. So, are there any questions? Yes.
We're going to talk about efficiency.
Yeah, so I don't think we'll have time for that, unfortunately. So one topic that would actually come up a lot in the second workshop is something called entropic optimal transport, which is a way of solving efficiently this problem of the Kantorovich problem. Unfortunately, we don't have the time for it, but I'm happy to talk a little bit about it offline. But in the workshop, actually, I'm sure people will discuss it much more.
Any other questions? If not, then let's thank you once again.